Hello, today I am going to do an example on matrix force method. This is a basic type of structure which we met. So this is analysis of structures using matrix force method example 1. Why we need matrix force method, why not, we need it is for find the reactions in statically indeterminate structures. Static indeterminate structure is a structures which we cannot find the reactions in the way which we always using to find the reactions. We cannot find the reactions here by only just using equilibrium method. Here I draw the structure which I am going to solve today using matrix force method. Step 1. Identify the actions to be determined. Determine the static indeterminacy of the structure and identify the number of redundants. Here I am doing a writing mistake and it must be number of redundants. Select the redundant forces and introduce sufficient releases to form a stable statically determinate structure. Now I am name them as A1, B1 and C1. And A1 is already done. As you can see, I have marked all the reaction in the diagram as you can see. Static indeterminacy of a two-dimensional beam is given by 3m plus r minus 3j. M is for members, here it is 2 which separate from the center. R is for reactions and which we have 6 here. Yes, 3 joints. So, static indeterminacy is 2 and which gives us number of redundants also 2. Which I am representing in a matrix. Here comes the third one. We need to select the redundants from these 6. I am selecting R1 and R2. Why? You will see in a moment. When we released R1 and R2, we can clearly see the released structure is a very familiar type of structure, which is a simply supported beam. It is okay to select any 2 as redundants and you can just follow the steps I am about to do. Here comes step 2. Determine the displacement at coordinates due to externally applied loads. Determine the actions due to externally applied load. You can see I am drawing the released structure and marking the coordinate 1 and 2. These coordinates are not any kind of load or bending moment, they are just positions where I release the structure. UDL is the externally applied load here. Here there is a vertical deflection d1 due to external load in the released structure at coordinate 1. And there is rotation d2 in coordinate 2. We can find these deflection using virtual force method. To find the deflection at coordinate 1, I put a unit load in the position where I need the deflection, which is coordinate 1, and the direction of the unit load is to the direction where the deflection is. This is the equation of the virtual force method. Here simple mx is representing the bending moment due to unit load, which I applied at a point which x meter far from left side of the beam structure. And capital Mx giving the same result but due to externally applied UDL. I need the reactions of the released structure as it is now simply supported. I can easily found those. I am trying to find the capital Mx here, so I am considering a point which is x distance far from left joint. Here, R is the shear force and capital M is the bending moment at that point. Consider anti-clockwise positive. I can found capital Mx as follows. Now simple Mx, which I mentioned before. First part is when x is between 0 and L. Second part is x distance between L and 2L, because not like first one here the bending moment equation differ in two members. I just found them using the equilibrium equations. Now, using virtual force method formula, by substituting the moments which I found, relative to x, we can found the deflection d1. Here I substitute them. The integration is doing as two parts because simple mx formula was differ in two members. This is the solution. Pause the video and try it yourself. If you are not familiar with virtual force method, I am hoping to do a separate video about it. Here we go again, rotation D2. To find the rotation D2 at the coordinate 2, we can use the virtual force method. First I put a unit moment in the direction where I need to find the rotation, and the point which I need rotation. I need those reactions, and I can find them easily. Here capital M is the moment, in anti-clockwise direction. From the x distance, far from the left joint. By substituting 1 and 4, in the formula, we can found the rotation due to externally applied load. Do the integration yourself and check the answer. I can write those deflection in a matrix. So a 2 is completed. As well as B2. This is step 3. Determine displacements due to unit values of redundance. Determine the actions due to these forces. Here mentioned unit 1 forces are not like the ones which we used in virtual force method. They are just representing R1 and R3. Actually we assumed these R1 and R2 is 1. Then, using superposition we find the exact values. F11 is the deflection, due to unit load, and F21 is the rotation due to similar unit 1 load. F12 is the deflection, due to unit 1 moment at the coordinate 2 representing R2, and F22 is the rotation due to same 1. Using virtual force method you can find those formula. I am not doing that part here, because it will extend the video more. Pause the video and try to do it, as we do it previously. And I hope to bring separate video about virtual force method, and I will do this part there. Somehow it is not belongs to matrix force method, it must be your previous knowledge. A 3 is done. And so, B3. Now, I can write those deflection in a matrix. Next, I can write those reactions in matrix form too. Finding those reaction is not so hard. Just consider the equilibrium. Downward negative. Upward positive. Step 4. Use the principle of superposition, and write the compatibility equations. Determine the redundant forces R1 and R2 by solving these compatibility equations. Here I draw the relationship of the things which we found earlier. This is the superposition. We have represent the same diagram with the combination of two diagram. Now, we can write compatibility equations. In the first diagram, at coordinate 1 and 2, deflections must be 0. So, from the right side also it must be correct. The rotation too. So, I can write the compatibility equations like this. To vertical deflection and rotation too. We know what are F11, F12, F21, F22. These are due to Unit 1 reactions, which we assumed earlier. So, to get the correct deflection and rotation we have to multiply by R1 and R2. D1 and D2 is due to external UDL that both are in right side of the equation. So, the sum must equal to 0. We can write in matrix form and solve it, like the way I am doing. We need inverse matrix. Do it yourself and check the answer. This is the answer. Step 5. Determine the remaining actions using principle of superposition. Please correct the answer. These WL loads is R3 and R4 value if we consider only UDL, and these are the answers for R3 and R4 if we only consider the Unit 1 reactions to R1 and R2. We need real value of R3 and R4, so we use superposition. We know R5 is 0. So this is the answer, and thank you very much for watching my videos.